In this video, we'll look at how to determine a polynomial model and what the data looks like if you're trying to find a model that is a polynomial for a set of data given. So down here I have a set of data, and I've already checked it to see if it was linear, and I found that when I subtracted all of these values pairwise, I did not get a constant difference, which means I know that this data does not form a linear model. I checked it for exponential as well by taking, as these independent variables went up by a constant amount of 1, I did not get the ratio to be a constant, or I did not have a constant factor change. 18 divided by 5 did not equal 55 divided by 18, so I knew it wasn't exponential. A power model also could be checked to see if, as your independent variable went up by a constant factor, say doubling, did your dependent variable have a constant factor, and that did not work either. So our next model to check is to look at how you determine for whether your data has a polynomial that fits it. A series of successive differences in the y-coordinates is what we want to look at for a polynomial. And so if we have our independent variable increasing by a constant amount, and we take differences between the y-coordinates, we look at what happens to the pattern of differences. The first difference is not a constant. Now I took pairwise and subtracted each of the new pairs to determine if they were a constant, and they weren't. However, my third difference did produce, the first time, a constant of 12. Now, the significance of the constant being 12 is not important for us. The important part is that it is a constant difference. And it took 3 differences for me to get that constant difference. And that shows me that this is a cubic polynomial. It's a degree 3 polynomial. Degree 3 polynomials will look like this setting: y equals ax cubed plus bx squared plus cx plus d. And I can see in the cubic polynomial I have a setting of 4 unknowns, which means in order to figure out what those unknowns are, I'm going to need to use 4 points. Now typically I'm going to pick the smallest points that I have in my set of data so that my numbers are as small as possible. So I'm going to choose to use the x values for 1, 2, 3, and 4 to create my system. I already did that below, where I substituted in the point. First point was the point 1, 5, and I put that at the bottom instead of at the top because I prefer to have my numbers be largest to the top and my smaller equation values to be at the bottom. So I plugged 1 in place of the x-coordinate and plugged 5 in place of the y-coordinate. I did that for all the other points as well. Now I'd have to solve this little system, subtracting the equations pairwise to drop out values until I finally find my coefficients a, b, c, and d. We've done that type of modeling before, so I'm not going to show all the work for that. But when I did, I ended up getting this cubic model. So a third-degree polynomial equation. So take our data, and if our data, we start subtracting the y-coordinates pairwise, the first constant difference that you have will end up being what the degree of your polynomial is. So that's how we tell if we have a polynomial model of nth degree.